Okay, class, we're looking at part 2 today for maximum or minimum of a quadratic function. I thought I would start out by looking at the Gizmo quadratics and vertex form. This is a review of the standard form vertex form equivalence, which we need to know about. We're trying to find the vertex, and in vertex form it's easily readable. So in looking at this investigate on page 25, we have 4 pairs of equations. The first in vertex form is shown at x plus 2 all squared plus 3. And you can see where the location of the vertex is at negative 2 x and 3 up on the y. If we show the polynomial form of this expanded, we see that it's equivalent to x squared plus 4x plus 7. Okay, loading up the next one, x plus 3 all squared subtract 4. We see the vertex here drops down below the y-axis to negative 3, negative 4. And again, the polynomial form there expanded is x squared plus 6x plus 5, which is equivalent to the matching equation for that vertex form function. If we explore the effect of using subtraction within the brackets, we're adding a negative value to every x coordinate. We see that immediately the vertex moves into quadrant 1, but more importantly, it moves to the right of 0, to the right of the origin. So the vertex here is positive 3, positive 4, and that in polynomial form is 2x squared subtract 12x plus 2, which is equivalent to the vertex form shown above. And lastly, the fourth combination would be a negative value added to x and a negative value added to the function operation. So after the squaring takes place, we subtract 7. We see here the vertex drops below the x-axis but is still to the right of the origin, and it's at 1, negative 7. The equivalent polynomial form there when expanded is what matches in that pair from 1D. So clearly the vertex form needs to be in the form a x subtract h all squared plus k, because the vertex is easily readable directly from the h value comma the k value. Okay, so we can use the sliders here and adjust them and just instantly see the effect on the graph. The vertex is unaffected, but more importantly, if we were to look at the parameter or the value that's related to the x coordinate, we see here that's just sort of the opposite effect. Where we see subtraction, it's actually moving to the left, but it's easy to understand if you insert a negative h value, you move in the negative direction. So the more negative it becomes, the more it moves away from the origin to the left. And when h is 0, it's be right on the origin. And then as it moves to the right, it's caused by a positive h value. With the k, that's a little bit more intuitive. If k is positive, it moves the vertex up. If k is negative, it moves the vertex down. And look at the polynomial form as I do this. There's no effect on the first two terms. So again, there, those parameters h and k are independently alter the vertex. H, of course, would affect the value of both the bx term and the c, because it's a constant, and so when that's expanded out of the brackets, it'll definitely alter the appearance of the polynomial form. K has less effect on it, and A has quite a bit of an effect because it multiplies through every single term. Okay, question number 2 in the investigate asks, why are the graphs of the functions in each pair the same? Well, of course, they have all identical coordinates. The third question asks, how can we rewrite the vertex equation in the form of the standard form? Well, that's just a matter of expanding, squaring the binomial, and then adding the constant term. 4 asks, how can we rewrite the standard form in the form of the first set, which would be vertex form? So that's what we're going to do here. So this one here, a simple example of a simple trinomial. We're going to approach completing the square as follows. In order to produce 4x from the same number, it would have to be obviously 2 and 2. And the corresponding term that would go with that as a perfect square would be 4. In other words, x plus 2 all squared would produce x squared plus 4x plus 4. Okay, now we don't have x squared plus 4x plus 4. We have x squared plus 4x plus 7. So we can't just sort of arbitrarily subtract 3 off of that to produce a perfect square. What we can do though is we can take the expression, remove the leading coefficient if it's necessary. Here it's not. Isolate those two terms by themselves. So now at this point it looks a little bit like partial factoring, except we've only factored out a constant, not an x term. The next step is going to be creating the term that's missing. The term that's missing is half of 4 squared. Okay, and then close the bracket and add the 7. Okay, notice that here we had 4, and half of that squared gives us the constant. Okay, so that's what we really need. Now, one thing I've missed here is, of course, we added it, but of course that would mean that we have changed the expression, so we have to also subtract it. So we also have to subtract 4 and then add our 7. The next step is going to be removing that fourth term, this one here, from the brackets by multiplying by 1. Okay, so the leading coefficient gets multiplied through, and we selectively remove the 4. It comes out as 1, 4. Okay, if the coefficient were other than 1, it would come out as multiple 4s or a fraction of a 4. Now at this point, we really have x plus 2 times x plus 2 in brackets. Okay, and I'm just going to emphasize that, and then we have plus 3. Okay, so now we have our perfect square. In vertex form would be x plus 2 all squared plus 3. And if this was our function, and here it was just labeled f of x, we would have the vertex currently, knowing that here h is -2 and k is +3. Our vertex is -2, 3. And of course, that function matches what was shown in the textbook for that pair in A. Okay, the next one, let's call this our function g of x here. We're going to complete the square again. So here, same leading coefficient of 1. So g of x becomes 1 x squared plus 6x, close bracket, plus 5. Now, completing the square, we need to create a perfect square. Before, we created the perfect square x plus 2, all squared. Here, it's going to be x plus 3. Okay, half of 6 is 3. So two values that produce 6 would be 3 and 3. And then, of course, the square of that would be 9. So x squared plus 6x plus 9 is the trinomial that we need to complete or create. So to do that, we're going to introduce the term that's missing, which in this case would be half of 6, which is 3, squared, subtracted as well. So we can sort of think of it as adding and subtracting the square of half of the middle coefficient, and then of course we've got our constant afterwards. So if we simplify that, we get x squared plus 6x plus 9. There's our perfect square. Now I'm going to remove that from, again, the brackets by multiplying it or distributing it, and it comes out as 1, 9. Okay. And then we have our constants, which will combine together. And at this point now I would factor the trinomial in brackets, and the appearance starts to change. And sometimes students wonder, you know, how all of a sudden did the square get there? Well, it got there because I took a factored form and I wrote it as a square of a binomial. Okay, so there, function g, and then I would state my h value is -3, my k value is -4, and so therefore my vertex is -3, -4. And again, g of x was x plus 3 all squared, subtract 4. Okay, now here we have a leading coefficient of 2. So first step, of course, I'm calling this function h, is going to be factor out the constant 2 from both the first and second terms. So that would be the common factored form, and then we have our constant at the end. Now again, here, off to the side, I can show that x squared subtract 6x as a perfect square. What needs to be subtracted? Well, x squared subtract 3x, subtract 3x, and then it would be again the square of -3. So here, the perfect square that we're trying to create is x subtract 3 times x subtract 3, or x subtract 3 all squared. So let's approach that as before. Create the term that's missing, which is the constant. That would be the square of half of -3. Add it. Sorry, half of -6, sorry, is -3, then squared. And then we're going to subtract -3 squared. So add and subtract. The net effect is we've really added nothing. So we have not changed the value of the expression. This is important. Add the 22. Cleaning this up a little bit, we're going to have x squared subtract 6x -3 all squared is +9. And then this is going to come out of the brackets as, maybe I'll just show one more step here, as, plus 9 subtract 9 plus 22. Now there are two -9s in that brackets, right? Because everything in the brackets is doubled. So when it comes out of the brackets, the other three terms don't. But when it comes out of the brackets, it comes out as 2 9s. Okay, when it was factored, it went back in as 2 times -9. So here we must have a -18 being combined with, and at this point, I'll combine some steps here, and I'll factor x squared subtract 6x plus 9. Two numbers that adds at -6 and, and then multiplied to +9, or -3 and -3. -18 plus 22 is +4. So again, I state my h and my k values. H is +3, subtracting +3 from x, and k is, ahead of myself here, this is 2x subtract 3 all squared plus 4. So therefore the constant h is 3 and k is 4, and so my vertex is 3, 4. All right, this last one here, I'd have you pause the video at this point, and you've seen 3 examples, and then I'm going to show all the steps at once and you can compare your work to mine. Okay, so here's my solution. On the side I've showed the perfect square. Running through my steps here, I'm showing lots of intermediate steps here, and that's going to prevent you from making mistakes as you get close to the end here. I go from the factored form to the perfect square form, and I state my h/k value and my vertex. As you can see, completing the square method relies pretty heavily on some algebra and factoring methods. It does connect to the quadratic property of transformation, because we looked at that gizmo showing the effect of moving the location of the vertex according to the h and k parameters. So there is some connection there, which is good. I don't really like methods where it's just too mechanical and not enough understanding, but this has a good balance, as did partial factoring. So just to summarize the method of completing the square on a standard form, that is function in ax squared plus bx plus c form. We have an example given here, and this one has a fractional leading coefficient. I believe this one is question 2f. So when you get to 2f, you can skip that one, and it'll have been done for you in the video if you copy these steps down. First step is to common factor the coefficient a from the first two terms. Now remember, with partial factoring, we removed ax, but here we just removed the numerical value. The result of that would look like this. Just to check your expansion, 2/3 times x squared is 2/3 x squared. 2/3 multiplied by 8/1 is 16/3 x. Close the bracket, and then we have 25/3 as our constant. The next step is to construct the third term of the perfect square trinomial and add and subtract half of b over a squared. So at this point now we have here this 8 is b over a, and when we take half of 8 and square it, we would get the square of 4, which would give us 16. So we're going to get adding and subtracting 16 within the square brackets, no change to the constant yet. Remove the fourth term from brackets by multiplying it by the appropriate number outside of the bracket, and that comes out as 2/3 of 16, which is 32/3. And Notice I'm just working in fractions here all the way through. Then we combine the numerical terms. The result will be the k, which is the y-coordinate of the vertex. Here we're going to have to employ common denominator, well, which is already present. So negative 32 plus 25 is negative 7. So our k value is negative 7/3. Also factoring the trinomial in the square brackets gives us x plus 4l squared, and the next step is just to express that perfect square in vertex form. And at this point we are done. The vertex stated is just easy matter of identifying the value of the h and the k, and in this case there's a slight change needed, maybe to go from x plus numerical value squared to x subtract numerical value squared. That makes it much easier to identify the h value as -4, and here the k value is just the constant. So there's the method of completing the square, and this is going to take you into day 2 work tomorrow, and you'll be doing, as we did before, some self-assessment and some drill and practice in number 1 and 2. Starting the feedback problem once you've finished all of those word problems, and then day 3 we're looking at applying these methods to derive the quadratic formula. Take care.